onto the electrical subsystems, which is the aspects that I am specialized in. Start off with the microcontroller selection. We decided early to utilize the ARM Cortex M3 microcontroller. The development board that we've been working on recently is this ARM development board from Leaf Labs. We are applying this presently to ensure that the processing capabilities that we need within the scope of our project will be met by this processor. Our determinant as of right now, our determination right now is that it likely will. However, there's some further testing to be done there. This processor was ideal based on its high performance. It also has a variety of low power consumption modes. It can go into sleep modes and a variety of other capacities. So it was very advantageous for us in that regard. The power plant of the battery would be the lithium iron phosphate cells that we are going to be using in a battery configuration of 6 cells, as Colin pointed out earlier. We chose this cell chemistry in particular for a variety of reasons. Lithium iron phosphate batteries have high energy densities with respect to other batteries. They're very safe over charge and discharge cycles of many, many cycles. They're relatively low cost compared to a lot of other batteries, and in particular, of particular importance to us is their ability to provide high discharge rates necessary for driving our motors as we can see them within the scope of the project itself. The battery pack, as it's designed presently within the iteration of the robot, is going to have a nominal voltage of 6.4 volts, sufficient to power our motors as well as all the peripheral accessories. A capacity of 10.2 amp hours, which will generate a life both under normal gate and of moderate intensity gate of approximately 30 to 45 minutes. Those estimations are done with calculations that I've estimated at this point in time. My idea is that we might be able to get life longer than that, up to maybe 60 minutes, although that is unconfirmed at this point. The power management throughout the entire unit is going to be handled through the power management unit that will be designed with a synthesis of application-specific ICs as well as team design solutions within the scope of the robot. It will be intelligent enough to distribute power to where it is needed and restrict power where it's not, protect against over and undercharging and voltage and current spikes. And in that way, based on the premise of it being somewhat intelligent, it will pull some of the processing requirements off of the processor itself. Cell balancing within the battery pack itself is going to be performed under a scheme similar to what I have shown here. This is a circuit diagram I pulled off of a PhD dissertation that I did research on that allows the distributing of power, active cell balancing within a 2-cell pack as I have designed it, in 2 cells in series. The sensors we plan to use vary and are of a great variety because of the wide range of applications we have within our robot. We have an ultrasonic rangefinder, simple RGB camera for object identification, accelerometers and gyroscopes for positional awareness, a plethora of current and voltage meters for power monitoring, temperature sensors both for ambient temperature as well as for component and cell temperature, pressure sensors in order to indicate if feet are on the ground and stuff of that sort, and compass and RF transceiver, possibly of Zigbee design. Those are not necessarily in the final iteration yet, however they are planned to be implemented so that we can test some of our solutions supposedly in the project. The nuts and bolts of the ferromagnetic system is still quite under design. We do plan to be using fluorescent tracer dies. I have an example of it right here, in fact, as well as pictures right here that were taken last night. The die is somewhat difficult to work with in terms of its concentrations, but it's highly desirous for the application of the project itself, largely based on its incredible stability as well as its EPA-approved safe in the environment. It washes away with great ease. While it doesn't look incredibly special here, we did learn at the beginning of the presentation I could do this, which demonstrates, this is a green LED, as you've seen already, green laser, yes, that allowed the absorption of this material in particular that I have in solution is within the green spectrum, both green and yellow. So as you can see, yes. Rather than just being an aqueous solution where the laser may pass completely through it, you can see that this solution in particular completely stops the laser. There's nothing being projected at all past it. It completely absorbs it and is somewhat eliminated by a bubble. That's difficult to see on that scale. If we skip back to the presentation, you can see that it fluoresces rather brilliantly under very specific circumstances, obviously quite not under what we're going to have in nature as we're performing the robotic system. But we're working between developing a synthesis of methods of seeing this so that we can apply it to the emulation of a ground system. Last point. And we're still undecided as to how we're actually going to see it. My hope is to be able to use fluorescent diodes or some solution of that type. However, that is likely to prove insufficient. So we will more likely be using the camera on the robot itself to be able to see this material.
So one of the most important things to consider when working with like robots are how it locomotes. And the stepping patterns that like robots or like animals use are referred to as gaits. And so, there's an easy example. If a horse is walking around at this kind of slow speed, it uses what's called a trot gait, where it lifts alternating diagonal pairs of legs and walks around using that. But when you bring it to a higher speed, it switches over to a galloping gait, where at some points all 4 feet are off the ground at the same time. Within insects, there are 2 big players in gait types, and those are the wave and tripod gaits. For a really simple example, if you've ever seen a millipede walk, where it has like 1 leg at a time kind of pick up and travel up the length of the body, so they all kind of go on a wave. So you can see right up here, the legs lift up and travel from the rear to the front. That's a wave gait. And the tripod gait is seen in hexapods, where there are 2 phases where the front and rear legs on one side of the body are lifted in combination with the middle leg on the opposite side of the body. And in addition, there are other non-periodic gaits where you can position each leg individually. That's typically used for really rough terrain. So to go with tripod gait, as I mentioned, it's 2 alternating phases of 3 legs being lifted. What's good about it is that it's stable while you're moving. It's statically stable, so that if you were to stop mid-step and 3 legs are in the air, you would still have 3 points of contact on the ground. You would be able to keep standing. But it's a little bit less so stable than the wave gait. But it is a faster gait as a result of moving 3 legs at a time. And this is what we would be using primarily for just walking around. And then the wave gait, it has 1 to 2 legs lifted at a time. Depending on whether you have a wave traveling up each side of the body simultaneously, or if you go up one side of the body and then travel up the other side of the body. So you have maximum stability while moving because you only have 1 or 2 feet in the air at a time. And the benefit of that is really seen robots or insects with more legs. But the problem is, since you're only moving 1 or 2 legs at a time, it's inherently slower than a tripod gait. So this would be used for rougher terrain, for more careful walking. Now, since we have the mechanical and physical parameters of the robot, and we have motions and gaits that we want the robot to be capable of performing, we now need to figure out what forces we require each of the joints and each of the motors to allow us to actually do this. So in order to figure out what we need to solve what's called the robot dynamics problem. And there are 2 forms of this, one called forward dynamics problem, where you start off with a given joint position for each joint, joint velocities, and then the torques that are present in each leg, and then in turn that will give you what your joint accelerations will be. But in our case, we're trying to solve the inverse dynamics problem, where we know what the joint positions are going to be at any point in time, we know what the velocities are going to be, and we know what accelerations we want them to be, because we're trying to emulate a predefined motion profile. So in that case, we supply those, and it's able to tell us what torques are required to actually do that. So typically it's solved using the Lagrangian equations, which are computed using the difference between the kinetic energy of each individual body in the system with the potential energy of each body in the system subtracted from it. But the problem with that is when you start putting together multiple bodies with multiple chains, such as in our case where we have one body with 6 different freedom legs coming off of it. That's 18 degrees of freedom right there, and 19 different bodies to work with already. So the algebra and the matrix multiplication starts to stack up pretty quickly. So in the course of our research, we came upon a system called Spatial Vectors. It was developed by Roy Featherstone, professor at the University of Australia. And the benefit of it is that instead of having separate 3D vectors and 3x3 rotation matrices, you instead combine the angular position and the linear position and velocities and forces into one 6-degree freedom, 6-degree vector. And so as you can see here, for the velocity vector, you have the first 3 elements are the angular velocities of a given body, and then the linear velocities relative to a given point O. And then for the forces, the first 3 elements are the moments about a point O, and linear forces along the X, Y, and Z axes. And then you can take these and combine them into a 6x6 transformation matrix, and we just build that using the traditional 3x3 rotation matrix. And this R tilde here, which is representative of the skew-symmetric matrix form of the linear displacement vector. And then since we have all these forces and velocities modeled in this 6-dimensional system, we need some way of representing the inertial and mass properties of the system. So this comes in the form of a, once again, 6x6 spatial inertia matrix. And so to generate it, you supply the inertial tensor, the moment of inertia tensor about the center of gravity, mass of the body, and then once again R tilde, which in this case refers to the vector of the leading to the center of gravity from the coordinate system defined on the body. This then combines all the equations of motion into one single equation where you have joint forces, joint spatial inertia matrix, which is a combination of all of the spatial inertia throughout the body, and the joint space bias forces, which depend on the positions and velocities of each of the bodies at the point. So now that we have the system set up, we need some way of actually computing it. And so we decided to use a recursive Newton-Euler algorithm, which instead of repeating multiplications of the matrices as you travel down a kinematic tree like you would use when using the traditional Lagrangian methods, the problem with doing it that way is that it's very computationally intensive and you repeat a lot of computations that you've already taken care of. So instead, we use recursion, where for a given body, I, the velocity of that body can be computed as the velocity of the parent in the tree, and kinematic tree, summed with the joint velocity of that specific joint, combined with the joint motion subspace of that joint, which in turn you can also calculate the accelerations, the external forces acting on the body, the force transmitted from the joint, and then the actual joint torques.
So earlier we briefly mentioned about this anthill. It's a central location for the anthill lets them bring objects that they're told to find. It also acts as a human interface, as we're referring to as the queen. It'll allow us to go into a computer and say, and search for a cylindrical object, or a cubed object, or an object of this mass. And that will develop slowly as the year goes on. It also acts as a central charging station, so when low on battery or power, each end can go back and charge itself up without any sort of human interactions. Some of our upcoming milestones. By the end of B term, we hope to have a rolling chassis, despite us not being a wheeled robot. So we're looking to have a lot of mechanics done, a big chunk of electronics done, not necessarily a lot of the programming. Beginning of C term, we want PCBs, PMUs, all that stuff printed out, so that we can begin construction and debugging of our first robot. And by the end of C term, have that robot complete. D term, we want to look at building 2 more additional robots, so we can start developing swarm mediators. Our project budget. Despite a lot of our parts being really inexpensive, they add up quickly. So, for example, as a motor and gearbox combination is only $50. However, we acquired 23 motors and gearboxes. That quickly added up to $1,500. If you multiply that by 3 robots, that's on pretty quickly. The next couple of weeks, we're going to be heavily pursuing funding. As you can see, we're a little short right now.
Just as a quick note, we are doing the ICC accomplishing identity, which if you're not familiar with it, it's forms of motion.